and graph them on the Ti-Nspire, then you are here in the right place. This is going to be a brief tutorial and you will understand how to deal with Taylor polynomials. So go to Insert, New Document, go to Insert and select Graph, not Calculator, that was a mistake. Select Graphs and then you will be in the graphing mode. And we're going to graph the e to the x function, exponent x. Here it is in big fat blue font. We can rescale if you like by moving the hand up and down. In fact, we can move the axis as well. And we can move the text out of the way. Just have to have a fine hand. Okay, so that's how we can rescale. And now we're going to click on Tab to graph a Taylor polynomial. Whoo! No, that wasn't nice. There's something lagging here. Let's try that again. We're going to click on Tab and unfortunately I have to wait quite a while. Here we go. No, that takes very long. Taylor polynomial of, we can actually write f1 of x, or we can write the function comma x comma 1. That's going to be the degree. 1 is a degree. Enter. Aha. This is the Taylor polynomial of first degree for the e to the x function. It turns out that that is really the tangent line at x equals 1. Let's go to a different screen. And if I type in Taylor exponential function x comma 1,
it's 16 hours.
That's good. I do get the function 1 plus x, the tangent line of the e to the x function at x equals 0. If I change the degree to 2, I will get the second degree term as well. And if I say type in 5, I get the Taylor series up to degree 5, 6 terms, because 1 is a term as well of degree 0. Okay, so when we graph it, going back to graphing mode, we're just graphing the Taylor polynomial, but we are not actually seeing the terms. So that's why I showed you those terms in a different screen. Alright, so let's continue. Degree 1, trying to go back to f2 of x, and my calculator is nervous, very nervous. Aha. Oh. Let's try that again. Click on F2 of X. Click the tab button. I get a blinking F3. Go to the right. Aha, F2. There we go. Now I'm going to change the degree from 1 to 2. And what I get after pressing enter is a parabola. It's basically a tangent parabola, not a tangent line, a tangent parabola at x equals 0. And we see that we get a better match near x equals 0 on the e to the x function. So now as I increase the terms, the degree of the Taylor polynomial, the match between the Taylor series and the function e to the x is getting better and better. Interesting. So, because this acts a little funky, I would like to increase the degree to, let's say, 4 or 5 or something even bigger. Okay. What if we go here to insert? Nope. Go to menu. Go to, wow, graph, option 3, function. Here we go. Don't go away. Okay, instead of second degree, we're gonna change it to, let's say, degree 6. Press enter. Aha. Degree 6 polynomial gives us a much better match than the degree 2 polynomial, as we can see here. Right? The graphs are lying literally on top of each other for a much longer stretch now. Okay, let's do a more extreme degree. Let's say instead of 6, we're gonna do 20. I get back here, change it to 20. And now you don't even see two different graphs anymore. The blue e to the x graph is perfectly covered by the degree 20 Taylor polynomial of e to the x. Now if I would go more to the right or left, I may see a deviation, but for our window here, it's a perfect match. Let's see when I change the scale to show larger values. Here on the left we see the red, the Taylor polynomial shooting up, and there's still room for improvement. Instead of degree 20, we would have to choose an even higher degree to have an even better match here on the left side. But that is certainly possible. Let's see what happens when we are even more extreme. And we're going to select a higher degree. $100 is our new degree. Enter. And we get an even better match. Very nice. If we look at the table values of the two functions, f1 and f2, we should see that we really have perfect matches. And only when we select large x values, we should see slight differences. Now you can see that it is really important to study the error that a Taylor polynomial has inherently. Taylor polynomials are approximations. They are not perfect matches of the original function. So here we can see, when you look at the decimals, 5205 and here 520508. I think that was a little bit, okay, 079 instead of 08. So there we get some slight differences in the 5th or 6th decimal digit. Anyways, now you have an idea of how to graph Taylor polynomial, how to change the degrees, and see what how good the Taylor polynomials match the original function. And if you increase the degree of a Taylor polynomial, your approximation of the original function gets much better. The Taylor command here on the Nspire can of course not only handle exponential functions, but if you enter, for example, sine of x, and let's make the degree a little bit larger, let's say it's degree 10, and then you get the 10th degree sine Taylor polynomial, the Taylor polynomial of degree 10 for the sine of x function, centered at 0. Now you say there is no 10th degree. That's correct. There is no even degree Taylor polynomial terms. Sine of x is an odd function, therefore all the terms have only an odd exponent. Now you can imagine what happens when we replace the sine of x by cosine of x. Cosine of x happens to be an even function, so we only have even exponents, and the denominators you recognize: 2, 6, 24, 120, 720, 1540, etc. Those are the factorials. Factorials of exactly the exponent. Exponent 5 means you have 5 factorial on the bottom. 6 factorial is 720. And notice that both series are alternating, plus minus plus minus. If you do the ratio test, you will of course find that both sine and cosine and also e to the x, this interval of convergence, are all real numbers. That is not always the case. But if you happen to have Taylor series with factorials on the bottom and powers on top, your interval of convergence will always be all real numbers. Thank you for watching.